speaker today. That's Aymeric from Ecole Polytechnique, and he will talk about conformal prediction, more specifically towards conditional coverage in multidistributional or multi-predictor setup.
Yeah, thank you very much. Do I need the mic? I think it's okay, don't worry, I speak loud. So first I would like to sincerely apologize for the delay. I had two meetings that ended up overlapping, and so I'm sorry that I had you waiting. I'll try to be as concise as possible and finish on time. So I'm going to try to take the hour to basically introduce part of what you are going to see this morning. Let me just check first. That works perfect. That works. This morning I have a first talk. I'm going to talk a bit about reintroducing conformal prediction, maybe from a simple algorithmic standpoint. I don't know if Vladimir is still in the room. Thanks, Vladimir, for the amazing presentation on Monday. I'm going to do things that are a bit more algorithmic in order to just make sure that everyone understands the key building blocks of our conformal methods. And most of what I'm going to present in the first part dates back to 2005 and Vladimir's book. So there's not much novelty into that. And afterwards, I'm going to dive into two different directions. One which is going to be about conformal prediction with missing values. It's something we looked at. Another one is post-selection validity, which is the setup in which we imagine that someone receives multiple conformal sets and wants to select one, typically the smallest one, right? So this is also going to set the stage for two of the presentations that we have later in the morning. I'm going to mention that, and the introduction is going to serve also for those presentations that are also connected to conformal prediction. Okay, so briefly, what's the setup in conformal prediction? So that's something that we already presented before on Monday. So typically we have features X and an output Y. And I'm going to consider the output in dimension 1 in my presentation. And I have a training sets. And my goal is to be able to predict at any unseen point, let's say yn plus 1. Let's say xn plus 1 is my features. I want to predict yn plus 1 with some kind of confidence, right? And the way I'm going to quantify that confidence level is by saying that I want that the probability that yn plus 1 is in the set C alpha at xn plus 1. That event has probability at least 1 minus alpha, right? So that's my key concept of validity here. It's what we're going to refer to validity, right? Saying that the set I predict around point xn plus 1 contains the true outputs with probability at least 1 minus alpha, right? And obviously, this is easier to achieve. I can just say that my C alpha xn plus 1 set is the entire set, so the entire set of possibilities for y with probability 1 minus alpha, and is empty with probability alpha, and I have that, right? But obviously, it means that most of my sets are just the entire sets. It's not very interesting, so it's not what we call informative. So typically, we also want C alpha to be as small as possible, right? And we can think of the Lebesgue measure in order to measure the size of the set if we're in dimension 1. And we can think of volume of the sets if ever we go into a setup in which the output lives in multiple dimensions, right? So typically the values you have in mind is typically alpha equals 0.1, and we call that a 90% coverage interval, right? Okay, so this is the basic setup, and there are plenty of ways to achieve that. And again, I'm just echoing what Vladimir said on Monday. I mean, there are Bayesian methods that do that typically rely on the model. One of the specificities of, distribution-free uncertainty quantification is that we want those things to hold basically independently of any model and independently of the data distribution. So I could come in and have a model which is poorly trained or well trained, and I still want that the sets I obtain from those models do obtain coverage. And I don't want to make any specific assumptions on the data distribution, right? And another constraint is that we want that to be non-asymptotic. We don't, again, some of the results we are going to recover are going to be typically asymptotic or valid asymptotically, but most of the things we want to have to hold in finite samples. So just for a fixed number of observations, right? So in some sense, this is the list of things we want to achieve. It's a hard list to obtain. And the one thing we're going to be a bit not too strong on is what we mean by that statement that the probability that yn plus 1 belongs to that set. I mean, what we mean by that is obvious, right? The one thing which is not obvious is what the probability is taken on. And typically the probability is going to be taken on both the randomness of xn plus 1, the randomness of yn plus 1, and the randomness of many of the things that were used to build the set C alpha. Okay, so that statement is typically going to be a marginal statement, which is going to make it a bit weaker that's something that could be strong. Okay? So this is our goal, right? And so the morning roadmap is my talk first. That started a couple of minutes ago, right? I'm going to do this short reminder on the basics and the two directions I have mentioned earlier. And afterwards we have two talks. One after the break first, we have a coffee break, and we have a talk by Sweb on multi-output conformal regression, and a talk by Maxime on rectifying conformity scores for better conditional coverage. So you can already see that those are two of the directions that naturally can arise. The first one is going to be about multi-output. The second one is going to be about conditionality, and they are going to fit in the same overall framework but tackle different directions. Okay? So I'm going to start by introduction, I should say. So I tend to be carried away, so I always put big pictures of my collaborators, not to forget them, right? So the first part I'm going to present is something we did with Margot. Margot is now at UC Berkeley with Ryan Tipshirney, and it's part of a tutorial that we presented last year at ICML. And so if you want a longer version, I think it's 2.5 hours, a longer version of the tutorial, you can actually find it online, and we're happy to share slides. So this is something that is a resource we're happy to advertise. And this is, obviously, I should say, mostly the work of Margot, who was and is still an amazing student, and hopefully is going to come back to Europe one day. Okay, so the introduction part, I just want to make sure that everyone understands how the most basic conformal prediction algorithm works. So there are going to be trade-offs in conformal predictions between efficiency and speed. So some methods are going to be very fast to implement, some methods are going to require more computational power, and some methods are going to rely on split of data, which is not very efficient statistically, while others are going to try to leverage the entire data set at once. So on the one side, on the one hand, the one that do the splits is going to be called split conformal prediction, and basically all what I'm going to talk about in the first part is going to be in the split case. On the other hand, there is full conformal prediction, which is also something Vladimir mentioned, which is far more expensive to compute, and that I'm not going to talk too much about, but also very interesting. Okay, so we're going to start. Split conformal prediction can be applied based on different information you get. So what I mean by information you get is that when you do split conformal prediction, you're going to assume that you obtain a model that is trained on part of the data set. So it could be you take the data set, you put some part of the data on site to train a model, or it could be you arrive somewhere and someone has an on-the-shelf model that I've been using for 10 years, and you want to transform that model that predicts a single value into something that predicts a set, right? So that's what you take on the shelf can be just something that predicts the mean, or can be something that is richer. And this is something I want to insist on. We're going to be able to leverage in that framework something that predicts a single value, something that predicts quantiles, or something that predicts a probability distribution, right? Even in a Bayesian framework. So all of that is going to be in the split framework, and I'm going to show you how to use just a single point predictor, or how to use quantile predictors. And I'm just going to say afterwards we could do far more things in that direction, and I'm not going to get further into the details. So I'm going to start by this simple case, which is the standard split conformal prediction with a predictor that predicts just a single value, right? And I have a small animation to show you exactly how we build the sets. Again, it doesn't show anything about theory, it just shows you how we proceed. Okay, so hopefully this is going to start. So I'm going to say I have a regression framework with a single feature as entry and a single output as output, right? So it's d = 1, and my output lives in dimension 1. I'm going to take my data sets, which we have seen for a minute, and I split it in 3 parts. First, in orange, the training part. On that part, I'm fitting a model, right? And now, that model, I'm going to try to evaluate the type of error it makes. So I'm going to compute what we call residuals. And here, residuals are just the absolute value difference between my points and my prediction, right? And I denote those residuals as SI, okay, so the ICE score, which is the absolute value difference, and calligraphic S, calligraphic, is the is the bag of all those scores. Now I aggregate all those scores. I'm going to add a value which is just plus infinity. This is just for purposes afterwards of having the correct result. And this is my set of calibration scores. Now from that set of calibration scores, I want to be able to predict given interval at any point. So I'm going to sort those calibration scores, take a quantile of those calibration scores, and I'm going to use that quantile to define the set. So how do I define the set? Now whenever a new point comes in, so xn plus 1, say maybe around here, hopefully around here, yes. Okay, so I have xn plus 1, which is a new point at which I want to predict such an interval. I'm going to do my prediction with my model mu hat, obtained from the training part, and I'm going to add and subtract my quantile of level 1 minus alpha of my calibration scores, right? And so that gives me a set around points, at point xn plus 1, around the prediction, and that set has the particularity that it's symmetric, and I'm going to claim that the predictive region I obtain when I do that is going to, that's the theorem, right? Is going to contain, on average, a fraction at least 1 minus alpha of the output points. So if I look at the points that I had kept in the test set, a fraction 1 minus alpha is within the band. Right? And now I can breathe. Okay. Okay, so I hope this was not too fast. For me, it was a little bit fast. Okay? And so this is, again, arithmetically very simple. What we're just saying is that for a given model, we can evaluate, in some sense, the typical distribution of the errors it makes, and provided that the points on which I test afterwards, let's say, have the same distribution at least, and we're going to need a bit more than that. We're not going to need IIDness, but what we're going to require is exchangeability, provided that those points, let's say, are ID, with respect to the calibration points, the typical distribution of that error, the difference between that point and the prediction, is the same as the one I had in my set of calibration scores. And so the calibration scores can be used in order to obtain, say, the quantile of the calibration scores gives me a set which intuitively at least works as a good set that's going to contain most of the outputs, right? I think that method, in some sense, typically when I present it, people say, oh, is that it, right? It sounds far, far too simple, right? So what can we say about that? Okay, first I can just restate rapidly, just for the sake of people that on whose computer the animation doesn't play, what the algorithm does. I split into a proper training set, a calibration set. I train on that set. Or again, that part could just be avoided if you come somewhere and you have an off-the-shelf model that you directly use. And on the calibration set, you get the predictions. You compute the conformity scores. This is the most important object, right? The sets of conformity scores that I'm going to leverage. And you compute the 1 minus alpha quantile of the scores. And for a new point, you output a set centered around your prediction and with basically that you correct with minus the quantile plus the quantile. All good? Feel free to interrupt me too, right? There's no rush, actually. Great. Okay, so this is a split conformal prediction, again, based on a very simple regressor. What can we say about that? And basically, we can say that if the data is assumed to be exchangeable, right? So exchangeable, by definition, says that a number of points are exchangeable if for any permutation, the distribution after permutation remains the same as the distribution of the n tuple, right? It's a weaker version of IIDness, right? If my points are ID, then obviously they are exchangeable, right? Moreover, if points are exchangeable, they must have the same distribution, but they need not be independent, right? And the toy case for that is to say that if I have, let's say, components of a Gaussian vector with constant mean, constant covariance, constant variance for each of the coordinates, and constant covariance between any two coordinates, then whenever I permute the components of that vector, the distribution remains the same. It corresponds to just doing a permutation of that matrix, right? And I'm not going to change the covariance of the vector, right? While at the same time, obviously, the components of that vector are not independent because the covariance is not zero, right? And it's the Gaussian vector. Right, okay, so if we have that assumption, then we have the validity that we talked about. So the validity says that if my points are exchangeable, right, And if I apply my split conformal prediction methods on my n tuple of points, xi, yi, y equal 1 to n, obtain a set C alpha hat, which is random, right? I'm going to insist on that, such that the probability that my output is in the set is at least 1 minus alpha. And this is a one-slide proof. Okay? So I'm going to give you the proof structure. I'm going to skip one part, that I also put in the slides as a bonus slides. It's a simple exercise, but this is very easy to prove, actually. Okay? And we even have that probability is also upper bounded by 1 minus alpha plus something of the order of 1 over the size of the calibration set. Okay? So in some sense, this is 90%, and this is 90% plus. And you can think of like, okay, I'm going to take 100 points in the calibration set, then this would be between 90% and 91%. And again, I have to insist that that probability takes into account the randomness of C alpha hat and the randomness of xn plus 1 and yn plus 1. It's marginal on everything. Okay, so how do we prove that? I mean, we basically rely on what's called the quantile lemma. That's the part I'm not going to prove, which is something that says that basically the probability that's out of n plus 1 random variables, un plus 1 is smaller than the quantile of level beta of u1, un, and plus infinity. So I just add that plus infinity points in my bag of values, right? The probability that this is smaller than this is at least beta. And at most, beta plus 1 over n plus 1, provided that everything is almost surely distinct, right? And again, we don't want to get too much into whether there could be equalities in those things. If there are equalities, you could just randomly split any ties. That would work out. Or you could add a very small noise that ensures that everything has density and that equalities happen with probability 0. So in some sense, whenever I say something like those things are almost surely distinct, I want you to think of, okay, we're just doing a random way of splitting any equality that could happen, and everything works out. So it's not, this is never a big constraint, right? And this also kind of makes sense, right? Again, if I had just written here that I compare un to the quantile of the distribution, right? Not something empirical, right? The quantile of level beta of the distribution u, then I would have had that property. And here it's just saying that I can have a finite sample version of that, which is actually valid. And here again, I insist that for that property to hold true, the probability has to be taken on un plus 1, but also u1 and un, right? Everything is marginally averaged upon. Okay, and now if I have that lemma, which again, I insist it's a simple slide that uniquely relies on exchangeability, then I can say the following thing, that if my points are exchangeable, and if my scores are defined in the way I defined them before, typically I had that my scores were obtained uniquely from point xi, yi, plus from using the model mu hat, right? But mu hat was obtained from the training set, which was not, independent from the calibration set, right? So those scores are also going to be exchangeable, right? And xn plus 1, I mean, those scores, I in the calibration set and I being n plus 1, are all exchangeable. And now I just have to rewrite that my points belongs to my set, which is the set we have described here, if and only if my n plus 1 score is smaller than the quantile, meaning that the set yn plus 1 belongs to the set is the same as the set, the events that yn plus 1 belongs to the set is the same as the event that Sn plus 1 is smaller than the quantiles of my calibration scores, which is exactly the event we had in mind here. Okay, so again, just rewriting what's my set, the condition that yn plus 1 belongs to my set as the fact that my n plus 1 scores is smaller than the quantile of my set of scores, I obtain the validity and obtain the theorem that I had written before, right? So again, this is all dating back to more than 20 years ago, and it just says we have achieved exactly what we wanted, right? This is distribution free. I have never used any assumption on the particular distribution that we had. This is a finite sample. This holds for any n, and I have no convergence. This is exactly true for any n, and yeah, this is what I was looking for, right? And in some sense, I would say it's something that is somehow natural. You take a holdout calibration set in order to define your sets, and you use the symmetry between your calibration points and your test point in order to achieve such properties. right? The nice part is going to be, okay, that's, this obviously works whether the model is good or bad. So if I compare two models, now the animation is the same one, but just comparing on the left-hand side a model which is a bad predictor, and on the right-hand side a model which would arguably be a good predictor, then when I do my steps, in both situations I'm going to end up with validity. I just have that on the left-hand side, all my scores are going to be much bigger, on the right-hand side much smaller, so my quantiles of my score are going to be much bigger on the left, much smaller on the right, and so the set I obtain is going to be much wider on the left and much smaller on the right, but at the same time, the fraction of points it contains is going to be more or less the same one, right? So typically on the left-hand side, I think I have a coverage which is 94 out of 100 on the empirical part, only 100 test points here, and on the left-hand side, 93 out of 100 points that are covered, right? But obviously, because I had a bad predictor, now my sets are much wider, right? And again, this shows you what we were aiming for, right? We're just trying to obtain something that achieves validity, but the size of the set is going to depend on the quality of the predictor. Okay? Great. Okay, so what don't we have? We don't have marginal coverage. Sorry, we have marginal coverage. We don't have conditional coverage. So I cannot say that the probability that yn plus 1 is in the set conditionally to xn plus 1 is 1 minus alpha. It's going to be one of the big limits that we discussed afterwards. So in order to have that, we would actually need something, and this is where we have a first obvious limit of that method for now. So what's the obvious limit that I have when I look at that way of building conformal sets? What's in some sense striking about that way of building the sets? What is something we don't like about that? Yeah, it's the same width, right? I mean, the width of the set is the same at any of the points, right? And typically, I mean, here the data set that I have represented is more or less almost stochastic in terms of noise, so maybe the length is okay-ish everywhere, but I could very well build a set in which the variance of the points here around the optimal model is much smaller than on the right, and then having a fixed width would be very problematic, right? And in some sense, having that the length depends on the points is actually a necessary condition to have conditional coverage. If I want to have conditional coverage, that is the coverage with respect conditionally to the value of xn plus 1 is 1 minus alpha, for most distributions I'm going to need that the width varies with the points. So I'm going to show you now how we can advance towards that, and how we can use all the what we call base predictors in order to have something that depends, at least has a varying width, so some kind of adaptivity. Okay, so this is the second method I'm going to introduce, which is called CQR. That was, I mean, it's typically referred to as something that was reintroduced by, or introduced by Yannick Romano in 2019. And again, it's a split method, right? We take our data set, we split it in 3 parts, but now instead of relying on something that predicts the average, we're going to rely on things that predict the quantiles. So I'm going to have 2 predictors, QR, quantile regressor upper, and QRL, quantile regression lower, which respectively try to predict the lower quantile and the upper quantile. The value of the quantiles we use actually doesn't matter too much. And now I just have to define, as before, what we call a conformity score. So conformity score, instead of being the absolute value to the mean, now I'm going to define something which has a sign, and the sign is going to be negative whenever the point is inside, and it's going to be negative the value to the closest quantile, and positive whenever I'm outside, and it's going to be just, again, the absolute value to the closest quantile. Okay, so the one thing I've changed with respect to before is the way I define the scores. But if you look at the way I have defined those, again, this is symmetric. I mean, this just takes into account xi and yi, so my set of scores is going to be exchangeable. And now I can do the same things. I have aggregated my scores, I have sorted my scores, and I take the 1 minus alpha quantile of the scores, and I'm going to consider the set of points at point xn plus 1. So for any test points I want to predict, I'm going to consider the set of points yn plus 1 such that the score at yn plus 1 is smaller than the quantile of the scores. So I take my point xn plus 1, I predict my 2 quantiles, and I'm going to output as my sets, my predictive sets, the set of y's for which the score for that particular y would be smaller than the quantile of the scores, which just basically corresponds to taking the quantile of the scores and adding it and subtracting it to the quantiles. Remember that this is a signed score, so now this is here in that case the quantile is positive, so I'm actually extending the set a little bit in order to create a band that now has a varying width and exactly again corresponds to the set of points for which the score would be smaller than the quantiles. Okay, so now what's interesting here is that again we're going to have the same marginal validity as before. So we're going to cover fraction 1 with alpha of the points, but we now have used different base information. We have used as basic information the quantiles and not the mean regressor. Great. Okay, so again, the one property we leverage in order to have the validity is that my set of points y plus 1, my output y plus 1 belongs to the set if only if my nth plus 1 scores is smaller than the quantile of the calibration sets. Sorry, of the set of calibration scores. And again, that gives me that marginal validity is ensured independently of the quantile regressor, independently of how well you fitted it, actually independently of whether the quantile that you used to fit was, let's say, the 5% quantile and the 95% quantile. You could decide to use the 30% quantile and the 70% quantile. Those quantiles are going to be somehow worse, but the correction that you're going to apply is going to ensure that you have the validity on average, right? And so again, a quick animation. This is actually the last one, almost the last one, I promise. If I compare two setups, one in which my upper quantiles and lower quantiles somehow create a band which is too large, and one in which the band is too small, what happens here is that all the scores are going to be negative. Here, about 20% of the scores are going to be positive. So here, my quantile of my scores is actually going to be negative, which means that my conformalization step is going to reduce the size of the set. While here, as in the example I had before, my quantile of the score is positive, which means I'm going to increase a little bit the size of the set, right? And so in both situations, again, independently of the quality of the fit, or independently of the quality or the levels for the quantile I considered, I have that I correct the size of my set. Again, here my correction again is additive, right? I just add the same thing or remove the same thing everywhere. And in one case, I increase the set. In another case, I reduce the set, right? Okay, so this leads us to say, okay, how far can you go with that? And you can actually go very far. You can do a bit of whatever you want. So you can use quantiles. You can use predictors for the mean and predictor for the variance. You can use, let's say, prediction for the distribution. So if you actually have an output which is the probability, what you predict is the probability of any output value given x, you can leverage that in order to build conformal sets. Okay, so three examples. The first one was the just standard SCP in some sense, the most naive one. The right-hand one is the one in which I use the quantiles just presented, and we could do things in between, which is now my prediction is going to be based on a mean regressor and a variance regressor, and my score is going to be defined as mu hat of x minus y divided by my standard deviation, and this is also, a function just of x and y, so the scores I'm obtaining here are also going to be symmetric, and typically the sets I'm going to obtain are going to look like that. Okay, now the sets are multiplicative. It's like mu hat plus minus the quantile of level minus alpha of my set of calibration scores multiplied by my estimated of the standard deviation at point x, right? And so in that case, I have my example, which is my example has very low variance on the left, so the estimation of the variance is very small, very large variance on the right, and so again, I have some kind of adaptivity. Okay, so it's already time to summarize. Again, I'm not here to give a full tutorial on that, it's just to reshape the introduction on what we can achieve and what we aim for. Conformal prediction comes as a very simple procedure that enables to create uncertainty around the predictor that you have. It has finite sample guarantees, it's distribution free, and it can leverage anything that you already had trained off. So mean regressor, quantile-based, probabilistic, etc. We don't have conditional coverage. We're going to talk a lot about that, so I have already insisted once or twice on that. And the coverage here to obtain that is marginal on calibration set and test points untitled. Right? And now very briefly, again, mostly to let you know where people stand and what people look at in those directions, I'm going to just briefly skim over a few 3 or 4 challenges that people have. The first one is conditional coverage. So what we would aim ultimately for is to have that statement hold conditionally xn+1 and conditionally on the calibration sets, right? This would be a much stronger statement. It would say that, I mean, we can think of a medical application. Someone comes to the doctor, you would actually, that whatever you predict for him, let's say the reaction it has to a particular treatment is a set of values that covers his particular or her particular output with probability 1 minus alpha on that particular patient, right? Not average among the entire population. That doesn't really, that makes sense, but it's a much stronger thing to have something that holds individual by individual. And obviously you also want that to hold somehow conditionally to the calibration set, but okay, this part you can somehow achieve, this part is much harder. So xn+1 conditional validity is going to be the topic of one of the talks. It's not possible in full generality. I mean, there are impossibility results, but you can try to approach that. You can aim for some kind of group conditional validity, which is an in-between. But calibration conditional validity, this is possible to have, right? Because basically, you can have some kind of like, you can have that probability is going to be at least 1 minus alpha. That probability conditionally to the calibration set is going to be 1 minus alpha plus minus something of the order of 1 over square root of the calibration set. Right, so provided that the calibration set is large enough, you can have a result, let's say, conditional to the calibration set. Okay, and I leave it here for Maxime to say more about what we can obtain in terms of conditional coverage. The second one is data splitting, right? That efficiency versus speed trade-off or computational complexity trade-off. Basically, there is that distinction. On the left-hand side, what I've presented is SCP, and on the extreme order, there's full conformal prediction, right? This one is far more expensive from the computational standpoint, but leverages all the points, while this one makes a single split, so it's much faster, but actually is, because of the split, we lose in terms of information from the data that we extract, right? And I'm actually going to come back to the jackknife algorithm at the very end of my talk, because we're going to leverage jackknife algorithm in one of the applications. Okay? And beyond single dimension output, shortest slide of the talk, right? I'm not going to say anything on that. So I'm just going to say that Sweb is going to talk about that afterwards. So this is one of the important challenges, how to go beyond just subsets of R. I should have mentioned that whatever we do applies to classification too, right? It can be applied to classification. Classification is just a particular case where you have, let's say, multi-class or binary classification. Both can be tackled, and there is no particular challenge into that, but multi-output is very interesting. And beyond exchangeability, I'm wondering if I should say too much about that. Obviously, one of the challenges is that we require exchangeability of the data. So how far can we go without exchangeability? I would say the story is always the same one. If you can estimate a kind of shift, so if you know that you don't have exchangeability because you have 2 different distributions, or your test point comes from a different distribution, if you can estimate how different the distributions are, so typically estimate the shift, then you should do so, and you have some kind of reweighting schemes. You have reweighting schemes that enable you to have validity under such kind of shifts. Same for label shift. If you can estimate the shift, then you should do so. And then otherwise, you can try to, I mean, you can come from the robust statistics approach and you say, oh, whenever my distribution varies in a small neighborhood of with some metric on distributions, then I can have some kind of distributionally robust conformal prediction. And then you can go to time series and online learning. And if you don't have any assumption about how your distribution varies, then you change the metric you're looking at. So in some sense, you're going to say, instead of trying to have validity at any point, I'm going to try to ensure validity on the long run, which is akin to regrets in online learning. And if you go towards a regret, then you can have guarantees that in some sense are much weaker, but in a setup which is much harder to. Okay, so if you want the full roadmap, this is everything we covered. This is actually shameless advertisement for the tutorial. Say that you could fit everything into that. Conformal methods, what they aim for. 3 main types of methods: splits, full, jackknife type. Different kind of scores. We have actually reviewed 2 of those, but we could extend beyond that. And 2 main directions but there are many more actually. Marginal guarantees on how to get to conditional, and beyond exchangeability. And that's basically what people have done. I mean, a subpart, but I would say significant subpart of what people have looked at over the last few years in the domain of conformal prediction. Okay? Any questions on that? I can take a short break to actually take questions on that. Oh, sure. Oh, yeah, go ahead. Sorry.
So first of all, like beautiful. Like I really love both the presentation and the content. So I don't understand what happens sort of when you go outside of the domain of your input. So like you have these wonderful plots where you have data from in some box, but what I'm curious about, what happens when you step outside?
You mean step outside, like further to the right?
Yes, go out of distribution.
Okay, so out of distribution, you mean that I obtain a point which is here, right?
Make a prediction out there.
Yeah, I mean, the guarantee is still going to hold, and that's why you see that the guarantee is only marginal, right? The guarantee, I mean, if you take a point here, and typically the model has never seen any points around here, I mean, so first we do assume that the points are exchangeable, right? So it's not like we take a point which is completely out of distribution. We just have a point, I mean, if you have enough points, we're going to see, in some sense, the entire space. But what typically might happen if you have a point which you had not seen before is that you might not cover it, but the probability of that is low. And so this is all going to be absorbed into your coverage guarantee, which is somewhere over here, right? Which says that the probability that you cover is going to be 1 minus alpha, and typically you're not going to cover the points that are very far away. But because this is marginal on xn plus 1 and not conditional on xn plus 1, this does not contradict that, right? Okay, so let me rephrase. In some sense, you're right. If you have a point which is very unlikely, let's say a point around here, then it's maybe you are not going to have it's likely you're not going to have the conditional coverage at that point. You might not cover at that point, effective point here. But because the guarantees we have for the moment are only marginal, the probability of those points that are exceptional is going to be very small.
Right. So I think I understand the math side.
Yeah.
I pretend that I do. I'm not sure I actually do. I'm just wondering what happens in practice. So it's just
in practice, okay. In practice, your predictor would extend, right?
Yes.
Your predictor you will have a predictor. Let's say for this one, your prediction for the mean would extend. You will have a prediction, and you would correct in the same way, and you would output a set. And the set.
If I look at the center plot.
The center plot. Here.
I say, I mean, just visually, it looks like if I go like predict, if the input is way to the right,
yes.
I'm going to be told that I should be very like reluctant to trust my prediction. If my prediction is way to the left, it looks like it's going to tell me that it's a perfectly certain prediction, just visually.
Okay. So yes, I mean, so what that says is that to the left, your predictive sets are much smaller. To the right, your predictive sets are much wider, right? It doesn't say that you expect that you are going to cover more here than here. Hopefully, your coverage is going to be 90% here and 90% here. Indeed, it says that, I mean, the prediction set that you have is much smaller, so you trust much more your prediction. And on the right, you're going to have much wider sets, so which means you trust your prediction far less. And you expect in both situations that in the best case scenario, the sets you output contain the true outputs with probability 1 minus alpha. So if you have a point which is far here to the right, typically you're going to have a much wider set, which says you don't trust your prediction too much. But you're happy with that in some sense, right? You're happy to have a large set, and does that make sense?
It makes sense. I'm mostly curious about the left side.
Oh, the left side.
Then it looks to me like
okay, so
told that you can actually trust your prediction.
Yeah, I mean, in some sense, it tells you that the predictive set you have is much smaller, so you trust your prediction much more. Okay. That's right. Yeah, no question over there.
Well, this might also be a stupid question. I'm also not from the field, but what does, in this context, exchangeability mean? I mean, it's clear to me what exchangeability means on the left picture, but what does exchangeability in the middle picture mean? I mean,
it's the same thing. It's the exchangeability we're talking about, the exchangeability of the points, right? It doesn't say, you would not be shocked if I said that the points here I've trained on are ID, right? I mean, in some sense, I'm not saying this is point number 1 and this is point number n. I'm just saying I have a bag of points, and I mean, in some sense, don't be bothered by exchangeability. You can just think of IDness. IDness is enough. IDness is more than enough in some sense. It's just IDness implies exchangeability. And I mean, I think typically it's just saying, okay, I have a set of points, and those points are ID, it's points of x, y's, and I learn from them. Maybe.
Yeah, but I mean, y is on x, small x, y is in a narrow band. I mean, I'm just trying to see what.
Okay, on small x here, what happens is on the small values of x here, right? The variance I have learned is much smaller than the variance I've learned on the right hand side. And typically that means that the predictive sets are output are much smaller than here. And okay, I think I missed what confuses you in terms of exchangeability of the points. The points are just think of ID points from which I learn, and I've learned that here my estimated variance is much smaller than my estimated variance here. And I'm just saying that from an estimator for the mean and estimator for the variance, I can build a set, and that set is going to have on average 1 minus alpha coverage. Okay. Well, that's it. All I'm claiming.
Yeah.
There we go. Okay, so I'm going to have time to cover one of the subsection parts, probably not the 2, but that's okay. I'm happy to talk about the other one offline. I think I'm going to go from the missing values one, mostly because I'm going to show you how we connect that to the jackknife at the end, which gives me an opportunity to say that there is going to be one last animation in the talk. Otherwise, no more animation. So this is again joint work with Margot, but also Yaniv, Romano, and Julie Joss, who are great colleagues. And it's based on 2 papers. So I'm going to talk about the setup where we learn with missing entries. So missing entries is something which is ubiquitous in machine learning, right? It's the famous cheese paradox, right? The more data you have, the more missing entries you have, the less data you have, right? So it's like, so it's the same with the cheese with the, I don't know if you do say that. In French, at least it works. So the more holes in the cheese there are, the less cheese there is. And so the more cheese there is, the less cheese there is. Okay, but maybe it's a French joke. I don't know. Forget about that, right? No big deal. Okay, so what typically we do is to encode the missing entries with what we call a mask. A mask just is an indicator of the positions at which I have not observed any entry, X. So this is my mask, this is my data sets, I have my outputs, and I have my entries, and some of them I have not observed. And statistically, it's challenging because it corresponds to some kind of multidistributional setup where each particular mask has a specific distribution. So I have up to 2 to the d masks and up to 2 to the d distributions. And the mask can depend on x or y, okay? And this is what we refer to the missing mechanism, missing data mechanism, right? So the most simple case, and actually in many situations the only one in which we can claim something, is the missing completely at random case, where the mask is completely independent from x. Okay, so that says that the missing entries you have happen at random. In some sense, it's a default in the sensor, right? We're supposed to record the temperature, didn't because it was faulty, no big deal, no dependence between the missingness pattern and the observations, or the features, right? And the other cases are more complicated. Typically, let's say in the missing not at random, the missingness is allowed to depend on the observed variables, and in the worst setup, missing not at random, it's all the rest. And this is what happens in most situations. If I ask you about your salary, the fact that you don't reply to that question depends on your salary, right? Which means that the missingness pattern directly depends on X, and that typically creates biases in the datasets that are very hard to correct. Okay? And also we can have questions about the dependency between Y and M, so the outputs and the mask, and typically the dependency conditionally to X or not conditionally to X. Okay, so why is that interesting? I'll just, in some sense, this could be the end of the talk. Why do I believe that setup is particularly interesting? I believe it is because I think it's a nice setup to study distribution shifts. Okay, so what we have fundamentally is that for each pattern, we have a specific distribution conditionally to that particular pattern. And those distributions are connected because you can argue or you can try to make algorithms that rely on the fact that neighboring patterns are going to have distributions that are closer from each other than patterns that are further away. And you can actually have reasonable links between the patterns and the uncertainty. So typically there's an underlying model. If I say that, you're not going to be surprised. I can say something like, oh, the more missing data you have, the more uncertainty in your prediction you have. And normally you trust that model. You should say, indeed, and this is only true, this can be shown to some extent to be true under MCAR assumptions and assumptions like that. The less I observe on my features, the more uncertainty on my output I have. Right? And those are the kind of things that inspired us on working on those things. We wanted to see, okay, how exactly we could leverage those things. Okay? So what do we want to obtain in conformal prediction with missing values, or more generally, uncertainty quantification with missing values? We want to predict, again, yn plus 1 with confidence 1 plus alpha, which is building a set such that basically I have that. Okay, and this is the marginal validity that we had before, so nothing new here. Now I want something stronger. I want mass conditional validity. We talked about going towards conditionality. One thing I could try to obtain is that this statement here holds conditionally to the mask, which says that basically in some sense, again in a medical context, you have someone coming in and you want to be able to predict something for that person, and you want that the coverage is valid independently of which features were recorded for that particular patient, right? You don't want that because you are, in, let's say, in a poor neighborhood where they don't have the top scanner or the top medical equipment, your coverage is not valid, while if you have access to more features, then your coverage is valid. So in some sense, I'm saying that I want the coverage to be valid conditionally to the missing entries, the set of missing entries, not to the values of the missing entries. Okay? So the first part, and the part which is actually easy, is to obtain marginal validity. And so, again, here I'm just going to try to describe exactly how I represent everything. I have my calibration set here, which has 5 values. So x1 is my first feature vector, x2 is my second feature vector, and I have my test points to the top. And again, in orange, although it's not very visible, it's orange, I have my missing entries that are visible. And the first thing I could do is what most people do in missing entries is impute. So I take an imputation function, which is basically a function that tries to fill in the gap, and obtain that new set, which is the imputed data set. And I'm going to claim the following thing. I'm claiming that for any imputation function which is learned and which satisfies symmetry, basically anything which would be independent from, which would be learned independently from the calibration set and test point would be okay, but anything that would be learned taking into account all those points in a symmetric fashion, and then the data set that I obtain after imputation is actually exchangeable. Right, so in some sense I'm giving immediately an answer to that. I'm saying, okay, whenever I do imputation, for almost any imputation function that you could think of, I'm going to get that the data set after imputation is exchangeable, and then I can do whichever conformal prediction algorithm that I want. Right? So typically I could say, oh, I'm going to now predict, I get values, I compare those values to my outputs. This is the first animation I had, right? I compare the output to the true value. This gives me a first score. I compare the outputs to the value. This gives me another score. I predict here. Oops. I take my bag of scores, compute the quantile of that bag of scores, obtain a set, and that's a perfectly valid, marginally conformal set. Right? And again, so this says that I could do that with CQR, I could do that with full conformal prediction, I could do that with actually any conformal method, just because after imputation my points are exchangeable, right? But importantly, right, this is, I just obtained the marginal validity. I don't get the conditional to the mass validity. But this is the first answer, and again, this does not even require that I have MCAR or anything like that. I just require that, I mean, this can be applied to any missing data pattern, even aggressive ones like missing not at random. So what I obtain if I do that in experiments is, okay, I do have, okay, marginally my coverage is going to be 1 minus alpha. So I'm happy with that. But now if I look at the coverage depending on the missing data pattern, I'm going to see that typically for some missing data patterns, so here x1 and x2 missing, I actually have that my coverage drops. which is exactly the opposite of what I want in mask conditional validity, where I want all the coverages to be at the same level. Right? So how are we going to fix that? In some sense, the easiest thing, whenever you have groups with respect to which you want to be valid, conditionally to which you want to be valid, you can split according to the groups. So we say, on my dataset, I have a feature that I want to be valid conditionally to. I split my dataset depending on the values of that feature. I create many subtasks, and I try to solve all the subtasks. This is okay, but typically, because I have 2 to the d different patterns, I'm going to have very, very few points if I split my dataset in 2 to the d different sets. So that I can do, and I can actually show that there are many, in some sense, negative results. In particular, my mask conditional validity cannot hold for any distribution P if I don't make strong restrictive assumptions. Okay, so typically, even if we assume that M is independent from X, even if you assume that Y is independent from M given X, I'm going to have results that say that if I have distribution-free MCV, then the size of the set is, with high probability, just infinity. So my sets are just the entire set with high probability. And this is, this echoes results on impossibility of group conditional coverage, and basically it says it's very difficult to obtain those kinds of sets. Okay, so that's the first limit. So we're going to have to assume both that M is independent from X and that Y is independent from M given X. So in some sense, we're just going to assume that the missing pattern is independent from the phenomena, okay, which corresponds to faulty senses in some sense. Okay? So how are we going to achieve that? The first attempt we could do would be the following one. I'm going to say that, again, I take my calibration sets, I take my test points, and I'm going to overmask. The overmasking procedure consists in removing the second and third feature here from the entire calibration set. And now I do what I wanted to do before, which is, okay, now that I've done that, I select the points that have the same missing entries. So now I can select more points, right? It's kind of a missing data augmentation of just creating new points that had a different missing data pattern, but because of my strong assumptions on the missing data pattern and its dependency with respect to the phenomena, I actually have that those points are representative points from this one. So I actually get that all those points are exchangeable and that they all have the distributions of xn, mn plus 1, and yn plus 1 conditionally to the mask mn plus 1. So this is, in some sense, this is good, but I still don't get, and again, I can apply now any conformal predictor algorithm. I'm going to get the results, but still I have typically few points in that set, especially if I have very few missing entries. So if my test point is fully observed, I'm not adding any points by that overmasking scheme into that. Right? What I would like to be able is to leverage points that come from actually different patterns that are not necessarily included into the first one. Okay, the second attempt is to say, oh, now I do the same thing, have my overmasking scheme, and I'm going to take a random selection of that. So let's say I keep those. One, right? And now what could I do with that? I could say, oh, okay, I'm going to say I do imputation, I do prediction, I compare those to the outputs, still in a kind of split conformal way, obtain my set of scores, I do the same at the top, so I impute, predict, and now I get that I want from that prediction and that set of scores to obtain a conformal set. But it's not clear how I should do that, because those scores, some of those scores come from points for which I had 3 missing entries, some of those come from points in which I had possibly even 3 other missing entries, and this point comes from only 2 missing entries. So if I try to take just this value and add and subtract a quantile of those scores, it's actually not going to work. We're going to have to try to do something a bit more precise. I'm going to explain exactly how we proceed. We cannot directly aggregate those scores. What we're going to have to do is something in which we try to compare apples to apples and potatoes to potatoes. So I'm going to take my point here, on which I have those missing values, my test point, and I'm going to predict on both. I'm going to obtain a score here by the difference between my prediction and the truth on that particular calibration point. And instead of obtaining that as a score, I'm going to create an upper bound and a lower bound from that. So I'm going to take that score and add and subtract it to that particular value. It gives me an upper bound and a lower bound. I do the same for let's say the third point. The third point now has 3 missing entries. So I want to predict with this one. I have to impute 3 entries and then obtain a score. What I'm going to do is that I'm going to first change my test point. I'm going to say, let me remove that particular value. And now that I have those 2 points that have the same missing pattern, I can predict, I can impute, then predict, obtain a score, and subtract and add that score to that particular value to obtain an upper bound and a lower bound. And I'm going to do that again and again. And for all points, I'm going to work pairwise. So any pair of points that I obtain here, I'm going to remove the points from the test points, remove some features in order to have the same pattern and do basically the same imputation and same prediction on both the calibration points and the test points. And now it means I can basically use all my calibration points and I'm going to obtain n lower bounds and n upper bounds. And the way I'm going to combine those is say I get a bag of upper bounds, a bag of lower bounds, actually the other way around, and I obtain a set which is the lower quantile of level alpha of my lower bounds and the upper quantile of level 1 minus alpha of my upper bounds. I'm claiming that if I do that, I do have a kind of validity. I exactly have that the probability that I might set conditionally to the mask is at least 1 minus 2 alpha. And the experts in the room are going to recognize that 1 minus 2 alpha as being the 1 minus 2 alpha that is typical of jackknife methods or cross-validation methods. So I'm going to show you what jackknife is and just mention why it's connected. So, again. So what is jackknife? Jackknife is the set in which you want not to do a single split, but you are going to do multiple splits. So what you take is your data set and you duplicate your data sets n times. And for each of the duplication, you are going to isolate a different calibration point. So here the calibration point is this one, here the calibration point is this one. Then you're going to train on all values but this one, which means that all your training or range curves are slightly different, right? They just differ by a single point. Now you use the calibration point, which is different, to obtain some kind of like tests calibration score, right? This blue point has not been used. And around the test points, you're going to add and subtract the calibration residual. Right? In some sense, it mimics a bit what we have done before, but the model which is underlying changes each time. And now what I'm going to do is aggregate the upper bounds and aggregate the lower bounds in order to build the set, right? I don't have a single, I have n different models, so I cannot just aggregate the scores and predict and add and subtract the scores. I just aggregate the upper bounds, sort them, take the 1 minus alpha quantile of the upper bounds, and then I do the same thing for the lower bounds, right, that I have obtained by each time subtracting that particular score to that particular prediction. I aggregate my lower bounds, I sort them, and I take the alpha quantile of the lower bounds. Okay? And now the set I obtained by taking that lower bound up to upper bound is going to be what we call jackknife plus. I should always say jackknife plus, not jackknife. Jackknife is slightly different. The jackknife plus set is exactly that set. And that set is guaranteed to cover, but is only guaranteed to cover, unfortunately, up to level 1 minus 2 alpha. Okay? So what we do here is connect what we have done with missing data with jackknife. In some sense, the way we connect the two is saying that the training we do without point number I is a random training that consists in picking a particular mask that we apply both to the test points and to the calibration point. And so there is a coupling argument between the training and the set of masks that we have observed that is the crux of the proof. Okay, and this, I'm going to skip the experiments, but basically this enables us to recover the mask conditional validity in both situations where we have few and many missing values. Anyway, so that concludes that part on missing entries. It's interesting to know that we can do conformal prediction with missing entries. Marginally, it's kind of easy. Conditionally, it's difficult. There are impossibility results. But with enough assumptions, you can come up with algorithms that connect to jackknife algorithm and that achieve validity. And in practice, they perform well even beyond those sets. And I'm sorry for being a bit over time, but I'm going to stop here.
Thank you very much for a very interesting talk. Are there questions from the audience? Yes?
It's just thank you very much for your very dynamic and pedagogical talk. Just to mention one thing, historical, that is the very basic method was used a long time ago by in reliability. It's called the Wilks method. Maybe it's good to mention that.
That's right.
Because after that, it had been popularized by the team of work, but it was in another context completely, and it's good to mention that.
That's right. Should I add that? Thank you.
Was one more question all the way in the back?
Yeah, thanks for your talk. I have a question around, when you talked about validity under covariate shifts, and you mentioned that you basically have to estimate.
I would say that once, if you can estimate, you should estimate. If you can model the shift and if you believe your model of the shift is correct, then you should do that.
Yeah, and I guess that's my question. Like, are you able to maybe take into account some form of uncertainty in that estimation procedure as well? And maybe my question is like, can you build almost like a hierarchical conformal type procedure? I'm really not familiar with the distribution.
No, I'm not super sure I understood the question. So you're saying that, say again.
So you're estimating the effect.
Yes.
Let's say of the target shift.
Yeah.
But are you able to then add uncertainty quantification on top of that estimation, like on that estimation procedure that can then follow onto the kind of point predictions and the sets on those points? Like in Bayes' world, the way that we do it is we put a prior and then we propagate.
That's a good question. Let me think.
I don't know if any work that does that.
Right, okay.
Yeah, I'm not sure. I don't think people have done that. It's a good question.
It's a very good question. I agree.
It's a very good question.
Should be done, in my opinion. But
Yeah.
I don't know of any work that does it. Maybe we take two more and then we move. Yes.
Sorry, I have one question. I was wondering, I see more and more work applying conformal prediction into semantic segmentation. Semantic segmentation, the pixels are not IID. And my question is related to the exchangeability.
Yeah, sure. Typically there have been a couple of work on semantic segmentation, and typically what we can obtain is that you assume your images to be IID in some sense, or exchangeable, and the pixels are not. So what typically you can obtain is like, again, some kind of marginal results on that. There's a good article, I think it's actually one of the case studies we had by Anastasios, Angelopoulos, and co-authors that actually does that in a medical context. And again, the big challenge is that you're not going to get conditional to the pixel coverage. So typically, it's possible that you overcover on simple pixels and undercover on difficult pixels, or even the other way around. And so typically, what you need to do is, do your best. So you try to have first rely on your best estimator you can have, and afterwards try to have some kind of metric for how conditional you are. So typically, a correlation between what you predict and the size of your set, or correlation between any measure of correlation between what you predict and do you cover or not. And this is this kind of things that I report. I think it's, again, there is an in-between. What you can, in theory, you can show that it's very difficult to have full conditional results. What you can do is do methods that go in that direction, as the ones we're going to see afterwards, and try to measure if they do actually perform well.
One last burning question, because we should give due time to the posters. Yes.
Thank you for the talk. I have a question regarding the evaluation of prediction intervals. You mentioned that in terms of the prediction intervals, you want the length or the width to be small.
Yes.
And I suppose that's related to something called highest density region.
Yes, absolutely. Okay, but then I'm going to step on the stones, or step on the toes of the next talks. I think this is exactly what's.
My question is, highest density region does not have a proper scoring. And in the sense that if you simply consider the width or the length of the prediction interval, the perfect prediction may not receive the lowest width. So for example, if you consider data with heterogeneity in a time series, say if there's a point where you have a spike in the variance, so the prediction interval for that time point is supposed to be really large. But I can be cheeky. I can ignore that time point. I put a very small prediction interval there. Then when it comes to practical evaluation, then my cheeky method can receive a very small average length.
Yeah, you're absolutely right. That if I understand what you are saying, and I think I agree with that. They focusing on the first goal we have is validity, the coverage. The second goal we may have is efficiency, the average length. But the average length and the conditionality, so having coverage x by x, do not necessarily go in the same direction. So if I understand the example you are giving, you could very well have that in a particular region of the space, you have a lot of dispersion, and your best strategy in order to minimize your average length is actually to not have coverage in that particular region. So it shows that there are multiple metrics you should look at. Obviously, marginal validity is one. What we say is the first goal. But then the second one could be minimal length on average. But the third one, or the second one, could be conditional validity. And there is a good argument to be made that the priority is conditional validity. And given conditional validity, you want the set that has the minimal length. Right? But if you don't think about conditionality, then you just say, oh, I want marginal validity, then you want smaller sets rather than larger sets. It's just a way to say, okay, but there are several directions in which we want to compare methods whenever we do conformal prediction papers or uncertainty quantification papers, and we should not just report the average coverage, we should try to report things that like the conditional coverage and the length in order to be able to compare things in an efficient fashion. But I agree with you with minimizing the average length is not always the correct strategy.
Thank you.
Excellent. Let's thank our speaker again for